Hello, my name is Tae Han. I'm a PhD student under the supervision of Professor Won-Suk Om in Acoustic Program of Yonsei University. In this talk, I will demonstrate the computation of the flow field in a flyer plate impact test using a newly proposed Hugonion scheme. Before introducing the Hugonion scheme and demonstrating its application, let me first explain what the shock wave is. A shock wave is a type of propagating disturbance of high pressure. It is characterized by a thin region called shock front, across which pressure, density, and other properties of the medium change discontinuously. Some familiar examples of shock waves are blast waves from explosions and sonic boom of supersonic aircraft. There are many applications utilizing or mitigating the destructive effect of shock waves, such as lithotripsy and blast shelters. In design of such applications, fast and accurate computation of shock wave propagation is needed. Hugonion scheme is a computationally efficient scheme for shock hydrodynamics, proposed by Jae-won Lee and Won-Suk Ohm. It is based on the idea of representing and evolving the flow field using a set of particle-like discontinuities called Hugonions. Hugonion scheme is a mesh-free method and does not involve any smearing of discontinuities. For 1D problems, the scheme has shown to be 10 times faster than the Goldknop scheme. To describe what the Hugonion is, we start from ranking Hugonion relations. These relations are mathematical description of shock waves and relate the pressure, density, and particle velocity across the discontinuity. There are three solutions to these relations, namely compression shock, rarefaction shock, and a contact discontinuity. Hugonions represents the three solutions to ranking Hugonion relations, so there are three types of them: S, R, and T Hugonions. They each represent compression shock, rarefaction shock, and a contact discontinuity. R Hugonion, or rarefaction shock, although mathematically legitimate, is a physically impossible solution due to the violation of the second law of thermodynamics. However, by limiting the magnitude of the rarefaction shock to order epsilon, the second law is then satisfied at order epsilon squared. An example of Hugonian representation of the flow field is shown below for a typical blast waveform. There are three particle-like characteristics of Hugonions. First is a ballistic flight. A Hugonion propagates at its own speed until it collides with another Hugonion. Second is an interaction. When two Hugonions collide, a new set of Hugonions emerges. Third is the annihilation. Not all Hugonions emerging from interaction have significance. Those with magnitudes much smaller than order epsilon can be neglected without degrading the accuracy. The computation procedure for the Hugonion scheme is shown in the chart. First, initial flow field is converted into a set of Hugonions. These Hugonions then takes ballistic flight. When the collision of Hugonions occur, a new set of Hugonions emerge through interaction, and small Hugonions are discarded from those. Then the Hugonion takes the ballistic flight and the procedure repeats. I will now demonstrate the computation of the flow field in a flyer plate impact test using the Hugonion scheme. The test setup is shown below. A tungsten carbide flyer is launched at a speed of 400 meters per second to a stationary steel plate. Since the flyer and the target plate is thin, it can be expected that multiple reflections and transmissions of the shock waves at the boundaries to occur. Here are a few assumptions. First, the flow field is assumed to be one-dimensional. Second, the strength of the materials are not considered. Third, the flyer and the plate make an inelastic collision. Here is the result of the flow field computation using Hugonion scheme. At the impact, high-pressure shock waves are generated at the flyer plate boundary. These shocks are modeled as S-Hugonions shown red. These Hugonions take ballistic flights to the end of the other boundary. At the free boundaries, they are reflected as a set of R-Hugonions. R-Hugonions then again takes ballistic flights and interacts with other Hugonions, giving rise to a complex flow field. In this talk, we briefly introduced the Hugonion scheme and illustrated its application using the flyer plate impact test as an example. Using the scheme, we are able to compute the complex flow field resulting from reflection and transmission of shock waves. Thank you.